Dear students, this is part 1 of your Unit 2 Linear Algebra 2 of 18 MA 41B course. In this lecture, we are going to study the orthogonal and orthonormal properties of vectors as well as study the orthogonal projections. For example, two vectors u and v belonging to the vector space R power n is said to be orthogonal if their dot product is equal to 0. As an example, if u equals to 1, 2 and v equals to 6 minus 3, you can clearly see that their dot product is equal to 0. Therefore, these two vectors are orthogonal in R square. And a set of vectors u1 to up belonging to the vector space Rn, it's said to be an orthogonal set if each vector is mutually orthogonal to every other vector. For example, the set u1, u2, u3, where u1 is 3, 1, 1, u2 is minus 1, 2, 1, and u3 is minus half, minus 2, and 7 by 2, is an orthogonal set. Why? Because you can see that u1 dot u2 is 0, u1 dot u3 is 0, as well as u2 dot u3 is 0. And a set of vectors u1 to up is said to be an orthonormal set if it is a set of unit vectors which are orthogonal as well. As an example, the standard basis elements of R power n, which are denoted as e1, e2 up to e power n, is an orthonormal set because the dot product of mutually vectors are 0 and each vector is a unit vector. So next we will look at what is an orthogonal basis. In the earlier classes you have studied what is a basis, and a basis of a subspace W of a vector space Rn is said to be an orthogonal basis if it is a basis as well as it is an orthogonal set. So the earlier example which we looked at was an orthogonal set, and also you can verify by checking the linear combination C1U1 plus C2U2 plus C3U3 equated to 0 implies C1, C2 as well as C3 to be equal to 0. Therefore, that decides that it is linearly independent. Hence, this set is an orthogonal basis of R cube. So next is an orthonormal basis. So the basis, which is also an orthonormal set, is considered to be an orthonormal basis. For example, the set v1, v2, v3, wherein v1, v2, v3 are defined like this, would be an orthonormal basis. Why? Because the dot product of v1, v2, v1, v3, v2, v3 would all be equal to 0. And also you can check that these three individual vectors are unit vectors. And also they would form a linearly independent vectors. Therefore, it is a orthonormal basis of R cube. So next we will move on to the orthogonal matrix. A matrix, square matrix in particular, is said to be an orthogonal matrix if the inverse of A and its transpose are both equal. For example, consider the matrix P defined as cos theta minus sin theta cos theta. If you find the inverse and the transpose, it is found that both of them are equal. Hence, we can conclude that P is an orthogonal matrix. Similarly, the matrix A given defined as below can also be checked to be an orthogonal matrix. So now one more observation we can make here. If I take the dot product of the first row with the second row, it would be equal to 0. Dot product of first row with itself would give you 1. Dot product of second row with itself would give you 1. And also if I consider the columns, dot product of the first column, the second column would give you 0. Dot product of first with first itself gives you 1. Dot product of the second with second itself gives you 1. So therefore, this is one observation that in any orthogonal matrix, the row vectors are orthonormal to each other as well as the column vectors are orthonormal to each other. So next we will move on to the orthogonal projections. So first we will consider a vector u in Rn and a vector y also in Rn. Here our aim is to resolve y as a sum of two vectors, one which would be a multiple of u and the other which is orthogonal to u. So here you can see in the example, so this is the vector y, it is projected onto the vector u. So it is denoted as y cap. So y cap will be some multiple of u, and this is the vector z, which clearly is orthogonal to the vector u. Okay, so here since z and u are orthogonal to each other, obviously their dot product would be equal to 0, and that's what here we have indicated. So the dot product of this is your z and this is u, dot product equated to 0, and on simplification it yields that alpha equals to y dot u by u dot u, and we can express y as a multiple of u. So y dot u, u dot u. So here y cap is called the orthogonal projection of y onto u, and z is the component which is orthogonal to u. So next let us consider an example to observe the above said things. So consider y equals to 7, 6, u equals to 4, 2. So here we have shown what is y cap, that is 8, 4, and z is -1, 2. So your y cap is the orthogonal projection of y onto u, so that you see here. So your u is 4, 2, y is 7, 6, and y cap is here 8, 4, and here z equals to -1, 2, it is denoted, this is your z, y minus y cap, and this is -1, 2. And clearly you can see that y minus y cap, that is -1, 2, and u, that is 4, 2, they're orthogonal to each other. So next we will move on to the orthogonal projection of a vector onto a space spanned by two orthogonal vectors, and the formula is given by y cap equals to this. So here you can see that this is nothing but the projection of y onto u1, and this part is nothing but the projection of y onto u2. And here we will look at the picture. So here imagine u1 and u2 to be your x and y axis in the space R cube. So here first we have, this is your vector y. First we have found the orthogonal projection of y onto u1, that is denoted as y1 cap. Then we have found the orthogonal projection of y onto u2, denoted as y2 cap. So this would be your y cap. So using the parallelogram law, this would be equals to what? y1 plus y2. So y1 cap plus y2 cap. And your y1 cap and y2 cap are nothing but the orthogonal projection of y onto u1 and u2 respectively. So this perpendicular distance, so this is y, this gives you the vector which is orthogonal to the both the vectors u1 and u2. Okay, so here this can also be considered, this suppose if I consider a point in space, the vector y minus y cap will clearly be the shortest distance from y onto the space spanned by u1 and u2. So that's what here we have indicated. So if I take the magnitude of this y minus y cap, that would give me the distance of the vector y onto the space w, which is spanned by u1 and u2. So here let us consider an example. Here I am asked to find the distance from y to w, where y is -1, -5, 10, u1 is 5, -2, 1, u2 is 1, 2, -1. So here clearly you can see that the dot product u1, u2, u1 dot u2, that gives us 5, -4, -1, that is equal to 0. So u1, u2 are orthogonal to each other. Now we want to find the distance from y onto w, which is spanned by these two orthogonal vectors u1 and u2. So if we find that using the formula, that is found to be -1, -8, 4. So this is your y cap. So next we need the vector y minus y cap, and that is given as 0, 3, 6. And the magnitude or the distance from y to w would be the magnitude of this y minus y cap, and it is found to be equal to 3√5. Okay, so this is all about the orthogonal projections. Thank you for watching this video.